So today we are going to be talking about two extraordinarily related topics, linearity and superposition. Okay. Generally speaking, in a circuits 1 level class, you would only learn about superposition, but I'm a weirdo, and I think that linearity is a very important property that we're going to reference multiple times throughout this class. So we might as well learn about it. And superposition is simply a part of linearity anyway. Okay. So what we are going to do today at the beginning here is we are going to be looking at a slightly different view of a circuit. And then we're going to apply what we are gleaning from this altered perspective to more conventional circuits, okay? So what I'm drawing here is what I'm going to call a black box system. Okay. The black box system literally just represents, in our case, some circuit where we don't particularly care about what's inside of it. So we don't care what components it's made of. We're only interested in its behavior, okay? On the left-hand side of our black box system is where we apply inputs. I'm going to consider a system that has two inputs. I'm going to call the first one x1 as a function of time, and the second input x2 as a function of time. X1 and x2 represent voltage sources and or current sources. So things that we use to electrically excite a circuit, okay? So we apply some sort of source to our system. And on the output side, we have our responses. Y1 of t and Y2 of t, where Y represents the response of our that is generated within our system due to our input. So this could be a current or voltage that we measure in our system, okay? Our system acts on our inputs based on what its transfer function is, where the transfer function h of x describes how the system acts on the inputs to generate the outputs. So in a linear system, the equation that governs how this thing behaves would look something like this. H of alpha x1 of t plus beta x2 of t is equal to alpha y1 of t plus beta y2 of t, or in a slightly more simplified form, H that's acting on our total input gives us our total output. Okay. So effectively, we apply an input signal, doesn't particularly matter if it's current or voltage, to our system. Then our system acts on that input signal to give us some sort of output signal. Okay. This mathematical expression here, you're never going to actually have to apply it or anything like that in this class, but it really tells us about two distinct properties that a linear system must adhere to. And these properties are the additivity property and the homogeneity property. And we are going to look at both of those. And if both of those properties are satisfied simultaneously, we have a linear system. Okay. So let's start with the additivity property. So the additivity property of linearity states that if several independent, I'm going to put a line under this because it's very important that we're dealing with independent sources here. So if several independent inputs are used to excite a system, the total response, the output, due to all of these excitations can be determined by considering each input separately while assuming all other inputs to be 0. Okay. So let's talk about how this can apply to a circuit. So let's take the following circuit where we have a 6-volt source, a 6-ohm resistor, a 10-ohm resistor, a 9-ohm resistor, and a 2-amp source. And the quantity that we are trying to determine is this current IX. We are going to solve this circuit in 2 different ways here. The first way is that we are going to effectively throw the kitchen sink out. Okay, this isn't a single node pair circuit. It isn't a single loop circuit. So we are going to develop some number of equations using Kirchhoff's current law, Kirchhoff's voltage law, and Ohm's law to figure out how to solve for that quantity IX, which won't be wildly difficult by any stretch of the imagination, but will be a bit tedious. And then we are going to apply the additivity property where we solve our circuit with each independent source on individually with the other source turned off and see if and how that aids our analysis, okay? So method number 1, KCL, KVL, and Ohm's law. I'm going to make a quick copy of this circuit. And we're going to paste it down here and talk about the analysis steps that we are going to take. So as I said, we're going to take a kitchen sink style approach, and that means I'm just going to throw everything at it and we'll see what sticks. Okay. So I am going to arbitrarily decide that there is a voltage drop across the 6 ohm resistor, positive polarity on the left, negative polarity on the right, and I'm labeling it V6. I am also going to say that there is a voltage drop across the 10 ohm resistor, positive polarity on top, negative polarity on bottom, and might be a voltage drop across the 9 ohm resistor as well, arbitrarily positive polarity on left, negative polarity on the right. There may be some current flowing through the 6 ohm resistor, which I'm going to call I6. The current flowing down through the 10 ohm resistor is already labeled as IX, so I'm not going to have to label it. And there's a current flowing to the right through the 9 ohm resistor that I'm going to call I9. So effectively, all of my voltages and currents in this whole circuit are accounted for. And so now we are just going to play around with things, okay? So the first thing that I'm going to do here is I'm going to write Kirchhoff's voltage law equation around this loop. Okay. So I will have -6 volts plus V6 plus V10 is equal to 0. And let's leave that alone for now. The next thing I'm going to do is I'm going to write KCL equation at this purple node. Just do that over here. So I have a current of I6 entering. So I can say that I6 is equal to IX plus I9. And I've written 2 equations, and I have, I think, 5 total unknowns at this point. Okay. So we are going to use inspection and Ohm's law to reduce the number of equations that we have here, the number of unknowns that we have here. So for example, I9 is the current flowing from left to right through the 9 ohm resistor, but because that 9 ohm resistor is in series with that 2 amp current source, there has to be a relationship between I9 and the 2 amps. What is it? Right, so I9 is equal to -2 amps. So let's update this equation and say that I6 minus IX is equal to -2 amps. Now let's look at that KVL equation on the left again. Okay. So we could express V6 in terms of I6, right? So V6 would just be 6 ohms times I6. V10 would simply be 10 ohms times IX. And when we move the 6 volts over to the other side of the equal sign, this is what we get. And so we've now broken this down into 2 equations, 2 unknowns that we can solve. So take your calculator out and solve it. We're going to be solving lots of systems of equations in this class, so we might as well get started on it. Okay. So I'm using a TI-36 going into my system solver, and this is a 2x2 linear system of equations. My coefficient for my first variable, which is going to be I6, is 6. My coefficient for my second variable, Ix, is going to be 10. And my constant term is 6. So that's my first equation. And my second equation, the coefficient of I6 is 1. The coefficient of Ix is -1. And the constant term is -2. So when I solve this system of equations, I get I6 to be -7/8 of an amp and Ix to be +9/8 of an amp. Anybody get something different? All right, so how difficult was this? Not wildly difficult, but I would imagine if I left you guys to your own devices, it'd probably take you a little bit longer to do it than I did, right? You'd get there eventually, but it's not exactly straightforward. We will learn methods very shortly that would make this more straightforward, but let's look at what happens if we apply the additivity property, okay? So method number 2. Sure. Yes, sir.
Can you explain like the sign convention on your first ACL? Because to me, it looks like IX and I6 would be going the same direction.
So I am using, let me do it in this color. This current in is equal to this current out plus this current out at this node. So that is formulation number 1, I believe is what we called it when we talked about KCL. So the total current entering a node has to equal the total current exiting a node. I could have also just said -I6 plus Ix plus I9 is equal to 0, or I could say I6 minus Ix minus I9 is equal to 0. They all mean the same thing. All right. So method number 2. Additivity principle. So the additivity principle stated that if we analyze this circuit with each independent source on by itself, while assuming all other independent sources to be 0, we can just add up the results of those analyses at the end and get the exact same answer if this circuit obeys the additivity principle. So I'm going to paste my circuit here. And I'm going to ask what is hopefully a pretty obvious question. How many independent sources are in this circuit? 2, okay? So that means we're going to solve this circuit twice. Once with the voltage source on and the current source off, and again with the voltage source off and the current source on, okay? As long as each independent source is on exactly once, it doesn't matter what the combination is. For this circuit, there's only 2 sources, so we're going to analyze it twice. If there were 3 sources, there are multiple different permutations of the ways that we could leave things on and turn things off and still get the correct result, okay? So let's start with voltage source on and current source off, okay? So if I turn a current source off, how much current is that current source supplying? Not a trick question. 0, okay? So what I'm going to do here is I'm going to replace my current source with an element, and I'm putting that in air quotes, that will make sure that exactly no current flows through that rightmost branch where the current source is. So I'm going to replace my current source with an open circuit. Because an open circuit guarantees no current is able to flow through that branch. So an open circuit is effectively the same thing as a 0 amp current source. Does that make sense? Okay. Now we are going to analyze this circuit for what I'm going to call IX prime, where this prime just designates that this is the first time we're looking at this circuit. Okay. So how do I solve for IX prime here? Sure. Yeah, Ohm's law is a perfectly acceptable thing to do here. So 6 volts divided by the total series resistance that our 6-volt source sees, which is 6 ohms plus 10 ohms, looks like 6 over 16 amps, or simplified very slightly, 3/8 of an amp. So that analysis was significantly more trivial than what we just did. That number is not what we just got because we're only halfway finished, okay? Now we're going to analyze this circuit with the voltage source off and the current source on. So how do I turn a voltage source off? Well, as you guys correctly inferred, an off current source supplies 0 amps of current, so an off voltage source must supply 0 volts of voltage. So what do we know that always has a 0 volt voltage drop over it? A wire or a short circuit. So we replace our 6-volt source with a wire. That's how we turn a voltage source off. And now we have this circuit to analyze. And I'm going to call this IX double prime because it's the second iteration of our circuit analysis that we're doing. Who has an idea of how we might solve for IX double prime? Current division. Absolutely correct. What we learned in our last class meeting can easily be applied here. So we have a known current of 2 amps that is splitting up between a parallel resistor network that contains a 10 ohm resistor in parallel with a 6 ohm resistor. And since we want the current through the 10 ohm resistor, it goes in the numerator like so. And we can throw this into our calculator. So we're going to have 2 times 1/10, 1/10, plus 1/6. And this comes out to be 3/4 of an amp, which is the same as 6/8 of an amp. And finally, we can say, because of the additivity principle, that IX that we were looking for, the current flowing down through the 10 ohm resistor with both sources on, is simply the sum of the current flowing down through the 10 ohm resistor with each source on by itself. IX prime plus IX double prime. And so this comes out to be 3/8 of an amp plus 6/8 of an amp is equal to 9/8 of an amp. Is this the same thing that we got earlier? Absolutely. Brody, how may I help you? All 2 amps of current flows through the 9 ohm resistor and then splits, right? So it doesn't split until after it's through the 9 ohm resistor. This is the additivity principle. And this particular circuit containing voltage sources, current sources, and resistors satisfies the additivity principle, okay? Now we are going to talk about the homogeneity or scaling principle. All right. The homogeneity principle states that if an independent input is used to cite a system, scaling that input by an arbitrary factor alpha causes the output to scale by the same amount. So let's investigate this by scaling both of our inputs by a factor of 2. So if our 6-volt source was instead a 12-volt source, and our 2-amp source was instead a 4-amp source, what we are expecting to happen here is that IX will be twice as large because we scaled our inputs to make them twice as large. So what's our analysis going to look like here? Literally the exact same thing that we did a few minutes ago. I'll scroll up and show you guys. The only changes that we are going to see in our analysis at all is that 6 volts is now going to be 12 volts, and that minus 2 amps is now going to be minus 4 amps. So if you solved this system in your calculator a few minutes ago, change those two constant terms and tell me what you get as the result. -7/4 for I6 and +9/4 for IX. So the number got exactly twice as large, which is exactly what we would expect. That is all the scaling property tells us. Okay, we didn't really go through the steps of this analysis. I'm trying to move through this a little quickly here. But what I'm going to do now is I'm going to create a table, and we're going to make a prediction. Okay. So let's just write here, using prior system with 12 volts and 4 amps yielded I6 is equal to -7/4 of an amp, and IX was equal to +9/4 of an amp. Okay, so I'm going to write a table here. On the left-hand side is going to be my inputs, and on the right-hand side is going to be my outputs. So the first time we solved this system, our inputs were the 6-volt source and the 2-amp source. And we saw that our output was Ix was equal to 9/8 of an amp. Then we solved the circuit with the 6-volt source on by itself and found that the output was 3/8 of an amp. Then we solved the circuit with the 2-amp source on by itself and found that our output was 6/8 of an amp. Let me just double check to make sure I got that correct. Yeah, so 3/8 with the voltage source on, 6/8 with the current source on. Okay. Next, we took our original input, 6 volts and 2 amps, scaled that by a factor of 2, and found out that our output did indeed double, giving us 9/4 of it. So what we're going to do now is we're going to put these things together. We are going to show whether or not this circuit obeys the additivity property and the scaling property simultaneously by scaling both of the scaling both of our inputs by different amounts and applying the additivity property to see what we would get, and then we'll do the analysis here, okay? So let's say that I scale my 6-volt input by a factor of -3, okay? So my input, I'd have -3 times 6 volts. What do I predict the output will be in that case? -3 times 3/8 or -9/8. Absolutely correct. What if I scaled my current source by a factor of 5? Then I would have 5 times 6/8, which is just 30/8. Right? Now, what if I have -3 times the 6-volt source and 5 times the 2-amp source applied simultaneously? I should get -9/8 plus 30/8 should be 21/8 amps. So let's analyze that circuit and see if it's true. I'm going to replace my voltage source with an 18-volt source, positive polarity on the bottom, because that's 3 times 6 is 18. And then because I'm scaling by a factor of -3, I need to flip the polarity of my voltage source. All of my resistors will remain exactly the same. Scaling my current source by a factor of 5 is going to give me a 10-amp current source. So, and let's just use the pieces of information that we need. This is V6, this is V10. This is I6. This is I9. So for our KVL equation, we are going to have 18 volts plus 6 ohms times I6 plus 10 ohms times IX is equal to 0. Rearranging that, we have 6I6 plus 10IX is equal to negative 18 volts. For our KCL equation, we have I6 is equal to IX plus 10 amps, or I6 minus IX is equal to 10 amps. Let's solve that system. Again, it's really nothing different than just changing those two constant values, but I wanted to show you that. So if we throw this system into our system solver on our calculators, actually, I made a sign error here, didn't I? Because I9 should be negative 10 amps. So that's going to put a minus here and a minus here. So I apologize for that. So if I solve this system simultaneously, what I get is I6 is negative 59 over 8 amps, and IX is positive 21 over 8 amps. So I was able to predict how this circuit was going to behave before I ever analyzed it. That's how powerful the concept of linearity can be. Technically speaking, using principle of linearity, you could break your circuit down into however many different circuits you need with each independent source on once, and you could treat every source as a 1 volt source or a 1 amp current source, and you'd still be able to get the correct answer every single time, okay? That's because of the way that a linear circuit behaves. So now let's take all of that information and look at what is classically called the superposition theorem in a circuit analysis class. I don't want to write it down, so I'm just going to pull it up on a PowerPoint slide that I wrote years ago. Just because it'll take too long to write down. Very last slide. Superposition principle states in any linear resistive network, the voltage across or the current through any resistor or source may be calculated by adding algebraically all the individual voltages or currents caused by the separate independent sources acting alone, with all other independent voltage sources being replaced by short circuits and all other independent current sources being replaced by open circuits. This is literally the additivity principle. The exact same thing, but using different words. So we technically already learned superposition when we were going through those other things in our discussion of linearity, okay? So this is really just telling us the rules specifically for a circuit. Each individual independent voltage source on once, turn all the other sources off, find the result you're looking for, and then add them all together at the end. That is superposition. All right, so we have an in-class assignment and a mini lab today. So I want to bring your attention to a couple of things regarding the in-class assignment. Let me find it here. I think this is how long it's been since I updated them. And this is number 5. All right, so in-class assignment number 5, I believe, is a single problem. This is the type of language that I will use on your exam. So this is why I'm bringing it to your attention. When I say something like determine the contribution of the 1 amp current source to the voltage Vx, that means I want the 1 amp current source on by itself. The 5 volt source should be turned off. So I expect you to be able to do this analysis, and with the 1 amp source on, that should be current division. 1 amp source on, 5-volt source off, you can do that with current division. For part B, where I ask you to determine the contribution of the 5-volt voltage source to the voltage Vx, that means the current source is going to be off, and you can use voltage division to determine that quantity very easily. For part C, there is no circuit analysis involved whatsoever. You simply add the results of A and B together. And then finally, for part D, we are effectively scaling things. So you don't actually have to do any circuit analysis whatsoever either. If you scale the answer for part A correctly and scale the answer for part B correctly and add those results together, that is the answer to part D. You only have to do any actual circuit analysis whatsoever here for parts A and B. If you're doing analysis for C and D, you did not take away enough information from this lecture. Okay, so this really shouldn't take more than 10 to 15 minutes tops. All righty, that is enough out of me. Work on your in-class assignments. I'd be happy to answer any questions you may have. Lucas. Sure, but there's really no need to write this down.